Hi, this is Barrett Givens, and in this video, we're going to talk a little bit more about sequences converging to a point. And in some previous videos, we've learned about how a sequence can converge, and if we're in the standard topology on R or R2 or Rn, then that concept of a sequence converging matches up with what we learned about in real analysis classes. But in other topologies, it can sometimes act very differently. And in particular, we've seen an example, the particular point topology, where a sequence converges and it converges to more than one value. And that's not something that can happen in real analysis. That's not something that happens in the standard topology. So this theorem gives us a property that is enough to tell us that if convergence is to happen, the convergence will be unique, okay? And that property is if your topological space is Hausdorff. So here's the theorem: unique convergence in Hausdorff spaces. Let X be a Hausdorff topological space. If a sequence x1, x2, dot, dot, dot converges in this space, then it converges to a unique point. Okay, it can't converge to more than one possible answer. It just has one thing that it converges to. And let's remind ourselves what Hausdorff means. Hausdorff means kind of a mnemonic is that Hausdorff means whenever you have 2 points in your set, they each get their own house that are separated. Okay, Hausdorff. So Hausdorff means whenever I take 2 points, let's say A and B, whenever I have 2 points like that that are different from each other, I can always find two open sets, U and V, where A is in U, B is in V, and U intersect V is empty. Okay? So whenever you have 2 points, you can separate them with open sets that don't touch each other. All right. And it's definitely true that the standard topology on Rn is Hausdorff. So this theorem would apply to the standard topology on the reals. Okay. Let's go ahead and prove this theorem. In general, how do we prove uniqueness results? Is to prove uniqueness results, you generally assume that you have two possible outcomes of something, and then you show that you get a contradiction from that. Or you show that the two outcomes are equal to each other, one or the other. Okay, we're going to do this by contradiction. So suppose capital X is Hausdorff, and the sequence X sub n, or X1, X2, you can write it either way, converges. For contradiction, assume it converges to two values, A and B. Okay, could be, if it's more, just pick two of them. Okay, but at least two values. So by the fact that X is Hausdorff, now I have two values, A and B, so I have this sort of picture, this Venn diagram on the left. Because X is Hausdorff, there are open sets, U and V, with A in U, B in V, and U intersect V empty. Okay? So we've taken our 2 points, we've applied the Hausdorff property. Now, the other thing that we could think about is we're assuming that the sequence converges. And so what does that tell us by definition? Well, if a sequence converges to a value, then that, by the definition of a converging sequence, is that for every open set containing that value, it must eventually be inside that open set. By definition of converges, so like on my picture, by the definition of converges, my sequence maybe is sort of bouncing around out here, But because it converges to A, eventually it has to just stay inside of U. But also because it's converging to B, eventually it just has to stay inside of B, inside of V. So the points of my sequence have to be, from some point on, they have to all be inside of U, but also from some other point on, they all have to be inside of V. So how can the points of my sequence be inside of U, but also be inside of V when U and V don't overlap at all? That's the contradiction. Okay, that's the contradiction. So that's what we want. We want a contradiction. So by definition of converges, there exists an N1 such that for all little n greater than or equal to N1, X sub n is in U. And there exists an N2 such that for all little n greater than or equal to N2, X sub n is in V. And let's let capital N be the maximum of N1 and N2. Then X sub capital N is in U and X sub capital N is in V. So just take one of these points that you know is sort of far enough along in the sequence that it needs to be inside of U, but also far enough along in the sequence that it needs to be inside of V. So this point is in U and it's also in V. But U intersect V is empty. So how can I have a point that's in both of them? That's a contradiction. And so the thing that I assumed to get a contradiction was I assumed that it converges to two or more values. So it can converge to only one value. Okay, so in real analysis, you might have actually learned this fact. Like there might have been a theorem or a proposition in a real analysis or in a calculus class saying if you have a sequence that converges to a point, if you have a limit of a sub n equal to L, then L is unique. And it might have been proven using epsilons and deltas. We could have instead proven it this way, but you'd first have to show that the standard topology on R is Hausdorff, which you probably don't want to do in a calculus class. But this proof is great because this proof proves it for R, but it also proves it for R2 with the standard topology, or it just proves it for any topology that happens to be Hausdorff. So this proof actually does more than the real analysis proof because it proves it for any topological space that happens to be Hausdorff. Okay? It also tells us, because we saw an example previously where in the particular point topology, we had a sequence that converged to more than one value. That tells me that the particular point topology can't be Hausdorff, because if it were Hausdorff, this theorem would apply. So the particular point topology is not Hausdorff because of this theorem, okay? And this also just gives us yet more evidence that being Hausdorff is actually a really good property of topological spaces, and we should like Hausdorff spaces. Hausdorff spaces are great, okay? And so that's really special. The other fact that we've learned about Hausdorff spaces is that in a Hausdorff space, singleton points are always closed, okay? And then this is another fact that is nice about Hausdorff spaces. All right, thank you for listening.